Number 15 says, in a jury trial, suppose the probability the defendant is convicted, given guilt, is 92%, and the probability the defendant is acquitted, given innocence, is 99%. Also, suppose that 60% of all defendants are truly guilty. All right, so here we've got a jury scenario, and this is something you'll see with probability trees. This the jury trial. It's a good situation to be represented by a probability tree. So what's happening here? So if you're not familiar with the language in a trial, um, and the way we're using it here, let's try to be really clear. So when we say that somebody is guilty, we mean they actually committed the crime. Okay, and if they're innocent, then they did not commit the crime, which is different than if they were convicted or not. Right? So if they were convicted, then that means they were sent to jail. But that doesn't necessarily mean that they actually did it. Right? And if they were acquitted, acquitted means they were not sent to jail, and certainly, they might have been innocent and gotten acquitted, hopefully, or they might have actually done the crime and be guilty, but they end up being acquitted anyway. So even though we're using four different words, right? Innocent, guilty, acquitted, convicted, there's really just two events, and then their complements. Okay, so we'll say C is that they were convicted. So that would mean that C complement is that they were acquitted or not convicted. They were not sent to jail. And then there's G. G is that they are truly guilty. They really did it. They did the crime. So G complement is that they are innocent. They did not really do the crime. Now you could set these up the other way. You could say like acquitted and acquitted complement, or innocent and innocent complement. But I think it makes more sense here to use convicted and guilty, and then convicted complement and guilty complement. Okay, so you can see I've got the makings of my tree here. What I did there at the top is I just wrote out the things that they told us in the problem as we read it, and we can fill those in where they need to go. So they told us that, let's kind of go ahead and read. Suppose the probability the defendant is convicted given guilt. So that's the first one I've got there. Convicted given guilt is 92%. Right? And the probability the defendant is acquitted, so acquitted means not convicted, given innocence, so that's not guilty, is 99%, 0.99. And they also told us, suppose that 60% of all defendants are truly guilty. So they said, okay, forget, convicted, not convicted, let's just guilty. So the probability that all the defendants walking in there, going into trial, let's say somehow we know that 60% of them really did do their crimes. Okay, so that's 0.60. And now it comes to setting up the probability tree, right, in part A, using a probability tree, and we've got this question. So we know we've got to set this thing up before we do anything else. Now, the question that I never got back to in the last problem, and maybe I'll pull that back, is how do we know how to begin to set up our probability tree, right? How do we know? And here you see probability guilty, probability not guilty. How do I know it's that versus convicted, not convicted? Well, in this question, um, especially laying this stuff out at the beginning, it makes it really easy. So we have to start with something we know. And they told us probability of guilty. So we can fill this in right away. We could not start with probability of convicted or probability of not convicted because we don't know either of those. They didn't tell us that. So because they told us this one, we know this is how we got to get started. In fact, there's a second way that we might realize that it's guilty or not guilty to start, because that's how these probabilities are set up. The way we're going to start, the next level will have the G, back here on the given. And the next level of the G complement will have the G complement in that second position there. So kind of two ways we can see it there. That's probably the easier way. Well, if I filled it out with C and not C, then I wouldn't be able to even get started. So it's got to be this. But then I can see it there as well, that it's the given G complement, which we're going to see in the next level. And something similar was going on back in number 14. So you can look back at that and realize, oh yeah, it had to be. We started with the probability of going to the review, because that's what they told us. In that problem 14, they said the professor estimates that 80% of the students will attend the review, and that's how we got started. Right, our first thing was 0.80. All right. So let's go ahead and fill this out. So hey, if this is 0.60, then what is this one? Got to be 0.40, because it's got to be 100%. Okay, then we go to the next level. And now we're going to say, all right, looking at the guilties, convicted given guilt, not convicted given guilt. Let's focus right here. We know convicted given guilt. And it's helpful to have written that out ahead of time. So we can just fill that right in, 0.92. So what does this one have to be? Well, 0.08, right? Because this is 100% of the people that are guilty. Some of them don't get convicted. They get away with it. Okay. And now down here, so these are the not guilties. Sadly, some of the not guilties still end up convicted. Convicted given not guilty, and not convicted given not guilty. And they told us this second one down here, that's 0.99, which means this has got to be 0.01. Hey, no jury trials are perfect. I'd say 1%. You want it to be 0, obviously, but that's just not reality, sadly. Okay. So now we go to the last level. Just trying to make sure I have enough room. Okay. And the last level for each branch, we take the combination of, the two parts. So here it's G and C complement, and then we'll have G complement and C, G complement and C complement. And to fill each of these out, we just look back at the two numbers and we multiply them. 0.6 times 0.92 will give us this one. Grab my calculator. 0.6 times 0.92. And okay, 0.552. And then G and C complement, so 0.6 times 0.08. Okay. Again, there's the not guilty, but they got convicted. Well, that's why we have an appeals system. 0.4 times 0.01, 0.4 times 0.01, because we know reality. And 0.4 times 0.99, 0.396. Okay. All right. And now maybe even just to double check our work, we could add all of these up and just be certain that they add to exactly 100. We didn't round anything, so it should add up to exactly 100. Or 1, and it does. Okay. Now what's interesting is we haven't even gotten to the question. We've just we've done the hard work. Let's answer part A. What is the probability the defendant is convicted? Okay, so we're thinking probability of convicted. So what do? We look at the two cases where they were convicted. 0.552, guilty and convicted, not guilty and convicted. 0.004, we'll add those together. 0.556. So out of all the people that go into this court, or maybe if there's a new person going in, what's the chances that you'll be convicted, no matter who you are, whether you did it or not? 0.556. And part B throws a bit of a curve at us. Let's check it out. Given the defendant is convicted, find the probability that he or she was actually innocent. Okay, we're really going to explore that convicted and but actually we're innocent situation. So you see all of my work here, but let's go through it. Here's what they're asking. Given that they're convicted, so given convicted, the probability that they were innocent, and innocent means not guilty. Right? So the probability that they are not guilty given that they are convicted. And we'll use the formula. Okay. Now, when you're looking at this, we're thinking, okay, we're only looking at the people who were convicted. So out of the people who were convicted, what are the chances that they actually didn't do it? So here's what we do. We look at the probability of being not guilty and convicted, and we divide by the probability of being convicted, right? The one in the second position. And we've got all this information right here. Probability of guilty and convicted was the 0.04. And we just found in part A the probability of being convicted, 0.556. So we'll take the 0.004, divide it by the 0.556, and this, I believe, I rounded. Yeah, I rounded that to three places, 0.007. So we can, and kind of look what happened there, right? So at the beginning in the problem, they gave us convicted given guilty, not convicted given not guilty, right? Given guilty, given not guilty. And in this question, they switched it. And, they've reversed it. So given convicted, you're like, oh, wait, but you didn't tell us anything about given convicted. It was always the other way around. Okay, but we can go and piece it together. We've got enough. These problems build on one another. I like those questions that build up, so we don't have to do extra work. Our previous answers allow us to get to these new questions quicker. I like questions like that. Okay, that's probability trees. In conclusion, there's one last page, about half a page there in the lecture. Let me discuss that just for a moment. Approaches to probability. So it turns out what we've been doing in this chapter is the classical approach versus what you see more in statistics, which we'll do later, the relative frequency approach. So let me just mention each. All probabilities calculated in this chapter have been done using the classical approach. And it's the formula, the probability of event A is the number of ways that A can occur divided by the total number of outcomes. And even things like, part B here really stuck to that same formula, right? What are the, if you're only looking at the guilty people, then the chances of not convicted given the chances of convicted, right? It's still the number of ways that A can occur divided by the total number of ways. And that assumes that outcomes are equally likely. Of course, we know that in the real world, outcomes are not equally likely. So this second method is actually much better, much better in the sense of where this class goes. A different method is often more useful in statistical studies. It is called the relative frequency approach and uses this formula, the probability of event A, is the number of times A has occurred divided by the total number of times the procedure was performed. So when it comes to more real world scenarios, we can't just say, all right, we can't compare it to a deck of cards or rolling a die. We have no idea what the likelihood of different outcomes is compared to others. So usually you take, like a survey or you do an experiment and you look at, okay, how many times did event A occur divided by the total number of times that procedure, was performed. Um, and we look at, like actual data that has really been executed. It's not a theory. There's no hypotheticals. Like we can see it for what it is. This is a good approach when the likelihood of individual outcomes is uncertain. One could perform an experiment several times or collect data. So that's kind of like the experiment versus survey. In this approach, it is best to follow the law of large numbers, that as a procedure is repeated many, many times, the relative frequency tends toward the actual probability. Um, and not something we're really going to dwell on, but that idea kind of remains that the law of large numbers means, okay, to really get a good idea of the likelihood then in the relative frequency approach, we need to do the experiment a lot of times. We can't do it maybe 10 times, maybe 100 times would be good, but ideally we could do it many, like thousands of times, if possible, to really get a good idea of the chances of the likelihood of certain events. Okay, just wanted to conclude with that, to really connect it to just how we're going to use probability in the rest of the course. That's our chapter.